I wish to give you a glimpse of the beauty and complexity of the work of the awardees in my lecture. And one of the things that I envy many things of number theorists, but one of the things that I envy is that sometimes it's so disarming, the simplicity of the statements that they have, that and they are so beautiful, like something like every number, every even number is the sum of two primes. I mean, like how could you possibly beat that? I mean, how could you actually do something simpler than that? So I will attempt at giving you the sort of naked beauty of the theorems that these three people have proved, and showing you that I can't quite possibly be as simple as every even number is the sum of two primes, but sort of the analysis approximation of that. Okay, so the key players in these two theorems that I have selected actually from the work of Tristan, Phil, and Vlad, which I think are the most significant theorems that they have proved in the area of incompressible fluid dynamics. So the theorems actually regard the Euler and Navi-Stokes equations that you've already seen glimpsed in the talk of Laszlo. So here you see the equations, which we're going to consider in 3 dimensions. So there's one condition, which is that the field U, which is the velocity of the fluid at the point x and at time t, is divergence free. And there's a second condition, so as already observed by Laszlo, so this encodes actually the balance of flux. And there's a second condition, which is given over here, which is the law of conservation of momentum, essentially. And the second unknown that you see, P, is a scalar function, and this is the hydrodynamic threshold. So what is this number epsilon that I have in front over here of the Laplacian of the vector field U? This is what is called the viscosity, and is a non-negative number. And if the number is equal to 0, that is the famous Euler equations, and if the number is strictly positive, that's the famous Navi-Stokes equations. Okay, so far so good. Now, the only thing I actually want you to know about these equations is that if you have a smooth classical solution, and you actually don't need that much smoothness. I mean, it's like a simple calculus exercise. If you have a C2 solution, you can actually derive a very interesting law, which is that the time derivative of the total kinetic energy, which is written over here, is equal to this quantity over here, which is called the dissipation. And in the case of Euler, since this number epsilon is equal to 0, this right-hand side would actually vanish. Otherwise, it's strictly negative, right? So for Navi-Stokes. Okay, so now let me get to the first theorem. So there is what is called in the literature Osiris Conjecture, although you might actually challenge that. I will come back to that. And so this is something that was written by Osiris in his famous paper in 1949, and that is the following. So consider the Euler equations on a 3-dimensional torus. So what is the simplest thing that I actually do on a partial differential equation? Well, I can actually plug in the Fourier expansion, right, of my function u of xt, which you see written over here, and then translate my partial differential equation into a system, unfortunately an infinite system, of ordinary differential equations for the coefficients. And it looks pretty nice, right? So the divergence free condition simply means that the coefficient ak is orthogonal to the wave number k. And the momentum equation becomes this very simple ODE. So the time derivative of the coefficient ak is given by this series, right? So because sort of there is an interaction of all the modes. Okay. And what you actually see is something already very nice. The pressure magically disappears. There's no pressure, right? So pressure is actually nowhere here. So it becomes a self-consistent system, infinite system of ordinary differential equations. And I've highlighted that, here there is this K, right? So the way, the reason why I have highlighted it is because there's a non-trivial computation that you have to do actually. Naturally here there would be something else, but I can actually stick a K. So naturally here there would be a J. But I can stick a K because I have this relation over here. So I can actually trade a J for a K. So why is that interesting? Well, because if you stare at this right-hand side, you will realize immediately that for it to be well-defined, it just needs to be in little L2. So if the sum of the square of the Fourier coefficients is finite, here we go. Since here there's, J and J, but here I'm dividing by values of J squared, the amplitude of this guy is exactly the amplitude of AJ. And the amplitude of this guy is exactly the amplitude of AK minus J, right? So it's summable. I can define the solution. Okay. Now, here's here's the what is usually called Osiris conjecture, at least in the mathematical literature. So, and this is actually written. So some of it is written in his original paper. So for every delta bigger than 0, there are solutions in this sense, right? So which are only square summable, which violate the energy identity and such that they satisfy this Hölder regularity condition. He actually calls it Lipschitz condition at the time. And on the other hand, if instead you have delta, which is negative, so if you're actually like reversing the sign of this, so you're a little bit better than Hölder 1/3, actually the energy identity is correct. This is what is called Osiris conjecture in the mathematical literature. And the beauty of it now is that it's actually a theorem, so you can prove it. So it was proved by Konstantin A. and Titi in 1994 that the second part is correct. So if you have enough regularity, you have energy conservation. But it was a great achievement by Phil in 2018. It's actually just the publication date of the paper. That the first part of the Osiris conjecture is correct as well. So this like magic number 1/3 is a threshold. It's a theorem, so it can be proved. And the naked beauty is that if you go, everything boils down in the end, what you can actually show is that yes, there is such a Fourier series which is satisfying this infinite system of ODEs and which is actually violating this energy conservation. Okay, so that's one of the theorems, so the theorem of one of the awardees. And now let me actually go back to Navi Stokes. So again, I'm actually going to manipulate the equation and rewrite it in a particular way, right? So I'm just taking the usual Navi-Stokes equation, the momentum equation, and I'm just like, putting the nonlinearity and the pressure on the right-hand side. And one of the things that you observe, like, in a nice situation immediately is that actually this mysterious pressure is completely determined by the equation through a simple elliptic procedure. So usually it's called the ray projector, even though this work of Ozine in 1927 is like 7 years before the paper of Leray that was cited by last week. So what you can do is you can think about this term over here as a projection of the nonlinearity divergence of U tensor U in a particular subspace of vector fields. And what is actually this projection doing for you? Well, since U is divergence free, this path is divergence free, but the nonlinearity is not. So the gradient of the pressure is just like, pushing you back into divergence free vector. So that's very nice, right? I mean, you see that here there's the heat equation, and here there's the right-hand side. And so it's very tempting to just think about this partial differential equation as the heat equation plus a forcing term. And the forcing term, on the other hand, is like related to the vector field U with this particular law, right? So if you look at it in this way, like it's very natural to write it like I write it here. So I know how to solve the heat equation. It's a little bit more complicated than just the sum of two primes is two odd primes is an even number, but it's very elementary in PDEs. You know how to solve the heat equation. You have a heat semi, okay, and then you have Duhamel's formula, and you can just simply rewrite your solution in this integral form, right? So this is just the Duhamel formula, and again, you could play the following game that we people in analysis like to play, but see in 1927. I'm not sure you could identify him as actually an analyst. He's a famous fluid dynamicist. So you see this makes perfectly good sense if you have an L2 function to multiply these two functions and get an L1 function. And then the heat semigroup makes actually perfectly good sense in there. So you can actually compute everything. You can compute everything and you can write down a new formulation of your equation, which is pretty elegant. And here's the Buckmaster Vicol theorem. Again, 2019 is actually the time it appeared. Ozine solutions are actually imposed in L2. Okay, so even though this transformation looks like pretty natural, if I'm just dropping any further assumption about the regularity of your function U, I'm just telling you take the bare minimum to write down your equation in integral form. Actually, it's imposed. So there are infinitely many solutions for each initial data U0. And the energy identity again fails for the vast majority of them. Okay, so some of them might actually satisfy it, but the vast majority actually fails. Okay, so this is the naked beauty of the two theorems. Like I hope you agree with me that very elegant and very basic mathematical statements that you can prove and which were somewhat surprising. So now, so what? Obviously, these are objects which you might not like too much, right? So, for instance, a solution of a conservative system which is not preserving the kinetic energy, it's actually reversible, so it can actually increase the kinetic energy, which is very puzzling. And you have this other, like, self-contained, beautiful integral formulation. But what we're just saying is that, if you draw too many assumptions on your function, like, it becomes bad. So what do? I mean, they're monsters. So there's like two possible psychological reaction to this. It's a monster. I actually don't even want to consider it. The other reaction is like, well, okay, so maybe it's a monster because I am not understanding the monster right now in a good way. Maybe, if I study it better, maybe I understand it. So let me just take, since it's very late, let me just take a curious way that, mathematicians in the past reacted to some monsters. So here is a famous quotation. So it's an outrage against common sense. So here's another famous quotation. I turn with terror and horror from this lamentable scourge. I'm not even sure that's the correct pronunciation in English. Somebody should tell me. And then here I'm giving away actually what really this is all about. So if Newton and Leibniz had thought that continuous functions do not necessarily have a derivative, the differential calculus would never have been invented. This is kind of sort of pushes me back to childhood. I mean, it seems like, one of the contests that I had with my friends when I was a kid on, who gives you actually the best insight, this sort of. So when did this happen actually? So these are two quotations taken by three famous mathematicians. So Poincaré is the first one, Hermite is the second, and Picard is the third. And these are the comments that they had on the famous example of Weierstrass of a nowhere differentiable continuous function. So, of course, like, from the point of view of nowadays, yeah, sure, there are continuous functions that are nowhere differentiable, but they're pretty common objects. I mean, if you're studying, for instance, a Brownian motion or stochastic PDEs, they actually come up all the time. So, what is the upshot of this? Well, the upshot of this is that, first of all, whatever opinion I might have actually on the topic, if Poincaré was wrong at a certain point in his life, well, so can I be, without being ashamed of that. And of course, the other point of view is that sometimes things look actually very surprisingly, and you would maybe shy away from them, but it's not necessarily the most accurate strategy. Okay, so anyway, so this was like, a half fun slide. I hope you had fun. And let me get somehow back to, some of the significance of these results, and like, let me dig in a little bit more into them and try to convince them that, maybe there's no reason actually to shy away from them. I mean, maybe there's some interesting things that we can actually learn, even though they're kind of some kind of monstrosity. So here is why the Osiris Conjecture came out. So Kolmogorov in 1941, he laid down a celebrated phenomenological theory of turbulence. And one of the postulates actually of this theory, even before you start actually making some conclusions out of it, is that if you have a typical turbulent motion of a fluid with low viscosity, the rate of dissipation is independent of epsilon. Okay, so here I'm just like saying you take the solution of Navier-Stokes and I just make this parameter change. So a solution of Navier-Stokes where this epsilon is changing, I'm looking at different solutions for epsilon which varies. And what he's saying is that typically, even though this time derivative of kinetic energy density is given by this formula over here, and there's an epsilon in front, typically, even if epsilon goes to zero, you're not expecting actually that this right-hand side is going to zero. You're expecting that it stays bounded away from zero. Here I'm just, putting a constant over here, but this constant is depending on some macroscopic quantities of the fluid. It's not like, some constant which is independent of anything, right? But there are, at least the way it should be phrased is that there is a reasonable subset of the space of solutions which typically should actually display this behavior. Okay, and here's what Osiris actually says in 1949. He rediscovers this idea of Kolmogorov independently, and he says, well, it is of some interest to note that in principle, turbulent dissipation as described in his paper could take place just as readily without the final assistance of viscosity. So he's just saying, well, look, if this is going to be independent of epsilon, I might actually just even put epsilon equal to zero and look for solutions of the Euler equations which don't have conservation of energy. And And that's what he's saying, but then he's more precise than that. I mean, then he says, well, in the absence of viscosity, the standard proof of the conservation of energy does not apply because the velocity field does not remain differential. That's what he's thinking is happening, right? And then he goes on and he says, well, in fact, it is possible to show that the velocity field in such ideal turbulence cannot obey any Lipschitz condition, as I told you, he doesn't quote it earlier, of the form modulus of uxt minus modulus of uyt less or equal than constant modulus of x minus y to the alpha for any alpha less than 1/3. He doesn't use that notation. That is my notation. I mean, he has lots of errors for any point, you know, x and y, which is kind of cumbersome. He actually doesn't say that above that, you know, sorry, this should be like, you know, bigger because it's the negation. So cannot obey any Lipschitz condition of the form in which alpha is bigger than 1/3. So he actually doesn't say that for alpha less than 1/3, one should have dissipative solutions. Like that is what people inferred by the fact that before he's discussing that it should be possible. Okay. And at the Fourier level, you just see what happens when I actually multiply, you know, my ODE by AK, a scalar multiply. I get just this ugly formula. And what is the upshot over here? Well, the upshot over here is now that before I had K fixed, right? But now I'm summing over K and J. Now I can't ignore this guy anymore. So I have a multiplication of 3 of these quantities. They depends on the various A's, but then I have this K, which is blowing up. So if I'm just assuming that something is summable in L2, well, this could actually blow up, right? And where is this 1/3 coming? Well, this 1/3 comes like presumably from the fact that I can distribute this blowing up exponent in each of the 3 coefficients, right? And so if I have like a Hölder 1/3 regularity, which would mean that when I multiply by K to the 1/3 my Fourier coefficients, I have some summability. Hopefully I can actually prove that this quantity converges. When this quantity converges, then it's a matter of, you know, some algebraic manipulations to show that it is equal to 0. You're not. Okay, so now, as I said, it is natural to think that something could go wrong without enough summability to make sense of the right-hand side, right? So if you just look at the naked Fourier series and, you know, the right-hand side is not converging, well, why should actually be conservative, right? So why couldn't this possible thing blow up? Of course, this is like what you would expect, but it's another story if I tell you, sure, but, you know, I want you to construct a precise solution to that infinite system of ODEs, which is pretty complicated, that actually displays exactly this behavior. That is a rather challenging question, right? And one of the things which makes it actually rather challenging is that usually in mathematics, methods to produce the existence of something, which goes through an approximation procedures, through an iteration, they usually produce something good. They almost never produce something bad, actually. So it's a kind of problem in which you're left with like, okay, so I want to show you that something goes wrong, and it actually goes wrong many times. But how do I do that? Okay, so these are getting me to the last 3 slides. So there are these H principle schemes, and H principle, as was already noted by Martin, is the name of the topic of the special year here. So now the solution of Field, Tristan, and Vlad are actually all limits of classical solutions, even though they're mysterious objects. They're achieved through an iteration procedure where actually everything along the iteration is a very nice, smooth function, smooth object. And only in the limit you see some degeneration. So for instance, if you actually look at the scheme which is used by Phil, you just are augmenting the Euler equation by a right-hand side, which you already saw actually in the talk of Laszlo, is usually called the Reynolds stress. It's kind of a defect to be an actual solution of Euler. It kind of measures the distance to that. And well, in a sense, you can think about RQ as a poor man version of the viscous regularization, right? So in Kolmogorov theory, what you would like to have is actually a solution where RQ is really given by this tensor, maybe for some epsilon q, which is going to 0. Okay, and then it would be a solution of the Navier-Stokes equation. And then if I had something like that, and the solution is like displaying this property that is converging to a non-conservative solution of Euler, of course, I have validated this idea that there might be anomalous dissipation. Right? So one key point over here, in all these schemes, what is actually happening is that if you add a lot of oscillation over here, so you're like, generating a sequence of solutions. So you think actually that the next solution is built up from the solution UQ. What you actually would like to do is to add a lot of oscillation. And these oscillations, they're actually exploiting the quadratic term and resonances so to cancel this right-hand side. It's kind of the opposite of what anybody with some common sense would actually try to do, right? So I'm perturbing the solution from UQ to UQ plus 1. What I try to do, I kind of linearize the equation. And so I let actually the linear term dominate and kill my error. Like, you know, this would be like, for instance, the typical, say, Nash-Moser iteration for the hard implicit function theorem. I'm doing the opposite. So I'm quadratizing. I'm actually treating the linear part as a mistake, as an error. And I want actually the quadratic part to win. And obviously, this can't lead to something which is good, right? I mean, it essentially tells you that you don't allow in this infinite dimensional space a Taylor expansion of order 1, right? Okay, so such type of schemes actually have been around for 15 years in fluid dynamics. Well, in fact, they have been around for much longer in geometry. So you could actually date back to the work of Nash in the 50s on the isometric embedding problem, a similar idea. But now you don't want to give up actually the paternity of this idea to the geometers, right? So to our good colleagues and friends. So let me boldly say that actually in analysis, we were doing that 150 years. Because after all, you know, Weierstrass is like the utmost example of the hardcore analysis guy. It's just like, you know, imposing all the epsilon and that on you. So you couldn't go more analytic than Weierstrass, I think. But okay, so aside from all these heuristical considerations, and a lot of optimism, why would you actually believe that such a scheme is actually able to capture the optimal threshold? So I just want to give you a glimpse of Field's major breakthrough, even though he has contributed actually to the field in several different ways. And this is just like, you know, singling out what seems like to me the most striking idea of his paper. And that is that it's always possible, and it's like the surprising thing, it's always possible to actually localize the support of this RQ. So you're given a solution with this RQ error, which is actually spread. You can actually localize it in bandwidth, disjoint bandwidth in time. That is what he calls the gluing step, the gluing technique. And what is remarkable is that the size of these time strips, it exactly matches the typical time scale at which the advection through UQ is actually well behaved, right? So which is given by the reciprocal of the derivative of the field you're affecting with. Okay, sort of fundamental, because that is actually what sort of eliminate a lot of like bad interactions in this scheme that you use then to actually eliminate the error. So it's a very beautiful and simple idea. Of course, the implementation is kind of complicated, but it's a remarkably clean insight on what you can do. And it's like, of course, one of the major points is even just to conceive that actually this is why I'm saying, like, you know, it is always possible. That was a very big surprise. Okay, now what is actually nice also about this is that even though it's a monster, there are actually some structural properties of Field's iteration that remarkably match some of the predictions of the K41 theory. So I'm telling you, this RQ over there is a poor man version of viscosity. But if it were the actual viscosity, lots of the kind of predictions of the K41 theory would actually hold. I mean, would actually be consistent with the system, with the iteration scheme that is producing. Okay, so now let me actually get to a little description of what is, I think, for me, like, you know, Tristan and Vlad's major breakthrough in their work on the Navi-Stokes equation. So, so now the H, I mean, like they realize that actually these H principal schemes can be run for Navi-Stokes as well. I don't know how many times actually have been asked this before their work in talks, and I've always said that no, I don't think actually that can be done. So obviously I was surprised when they actually showed me that this can be done. And what was the like, you know, what was the rationale behind this? Well, the rationale behind this is that the H principal schemes that I told you always like make, you know, this guy win over any linear part, right? So, and when you have Euler, so when this one is not there, you just see that, you know, the most derivatives you have is just one derivative, and it's happening also on this nonlinearity as well. But now it looks like, you know, pretty crazy. It was crazy before, like, you know, to let the quadratic term win over the linear, but it seems even more crazy to let it win over a linear term which has more derivatives than the one which is quadratic. but it's possible. And why is it possible? So again, this is like just singling out among several contributions to the field what I think is like the most remarkable realization that they had. What it is possible is that if you at each step make a non-uniform perturbation, so if the perturbation is very peaked in certain regions, well, the quadratic term, of course, is really, really large because you have an infinity or an almost infinity that you multiply by itself. That is really a lot. And even though here you have, two derivatives and you have a linear term, still you can actually offset the loss in the derivative with the fact that this function is much less peaked. And so you can actually let the quadratic term go. Now, even this idea actually matches remarkably a well-known concept in the literature about turbulence, which is called intermittency. And that is that the Kolmogorov K41 theory, in fact, is not the most accurate predictions that you can have about turbulent fluids, but turbulent fluids really display some sort of local intermittency behavior. Okay, so now Tristan and Blatt's paper actually opened the possibility to tackle some problems which I think looked completely untouchable before from the experts. So let me just give you a flavor of this. So this is a famous theorem by Gladyshenskaya, Prodi, and Serin in the 50s. So take exactly the same formulation of the Navier-Stokes equation that I gave you, right? So this crazy formulation in which you're actually writing as an integral equation, okay? So I just told you U is square summable. So the square of U is integral, okay? And then the equation makes sense. So here is the magic. If actually you allow me to raise it to a power 5, then not only the solution perfectly makes sense, but it becomes regular. It's actually a classical solution right away. And you smooth. This hopefully makes you appreciate, how subtle it must be to actually use the L2 summability compared to the L5 summability, which is obviously not possible in that construction. Okay, so in fact, there's a whole range of exponent under which this theorem is correct, and this is what is called the Gladyshenskaya-Prodi-Serin line. What is, for instance, very remarkable is that it has been proved very recently by Cheskidov and Luo. And in fact, because you see there's a big gap between 5 and 2, but if you go to the two endpoints of this line, actually they're really optimal. So you have the regularity as soon as you are above, but you have the possibility of constructing counterexamples as soon as you are below. Or, it depends on whether you're looking at this number or the reciprocals. I mean, the below and the above. Okay, so let's say the below is bad, the above is good for me. Okay, that's it. That's all I wanted to say. And with this, of course, I want to congratulate Phil, Tristan, and Vlad about this.
Now, I see Thomas and myself on the screen. Is there a chance we can get Phil on the screen? Phil, I'm hoping you're there. Can you turn on your camera and your microphone, please?
Hello, I'm here.
Ah, excellent. Ah, very good. Hi. Glad you could join us, Phil. Now, can we get him back? Sure. There you go. Ah, right. Okay. So now, ask the other two prize winners. Tristan, do you want to? Tristan and Vlad. Phil, do you have your medal?
Yes, I do.
Ah, you brandish it.
I can.
Oh, very good. Chairman of the Board of Directors of the Clay Mathematical Institute, Thomas Clay, to give prizes to our other two prizes in alphabetical order. Yeah, so, and just to remind you, this is the 2019 COVID delayed Clay Research Award that's made to Tristan Buckmaster, Phil Isett, and Vlad Vicol in recognition of the profound contributions that each of them has made to the analysis of PDEs, particularly the Navier, Stokes, and Euler equations. I'll ask the prize winners to say a couple of words if they'd like to, in alphabetical order. So Tristan first.
Well, it's really a great honor to receive this prestigious award. I'd just like to thank my beautiful wife, my angelic Matilda, who's on the screen. I'd like to thank my family, my dad, my brother, my sister. I'd like to thank my longtime collaborator, Vlad, who has put up with me for many years. I think he often will get a email from me, which I sent to him on my phone in the subway in Manhattan with some cryptic idea. I'd like to thank my uncle Latsikovac, who convinced me to switch from computer science to mathematics, and Margaret for supporting me at that time. I would like to just thank some mentors I had through the years. Robert Bartnick at Monash, John Hutchison, and you, Herbert Koch at Bonn, Laszlo, my supervisor, Camillo, of course, who supported me throughout my professional career, Jalasha Tai took me under my wing in NYU, and Alex Linesco in Princeton.
Oh, would you like to say something?
Did you ask me?
Yes.
Okay, yeah, I have a little speech. Yeah, so thank you so much to the Clay Mathematics Institute and to Thomas and Camilo for this award presentation, and to Martin Bridson and Naomi Kreker for arranging that I could attend the event virtually. I'm very honored to receive the Clay Research Award, and congratulations to Tristan and Vlad for the recognition of their outstanding work. I really wish I could have attended the conference in person. I have great memories of being a graduate student in Princeton, and I love to visit, but hopefully there will be a chance for that in the future. I want to thank several people who have helped me along the way. First of all, I want to thank my thesis advisor, Sergio Kleinerman. It was Sergio who first encouraged me to study the work of De Lellis and Sekal-Hidi and to get into the area, and he has been very supportive and excellent mentor for many years. I also want to thank Camillo De Lellis and Laszlo Sekal-Hidi for their fundamental work in the field that my work has built off of, and I want to thank my wife for all of her support. And just say, and when I think about Osiris Conjecture, I find it really striking how the different ideas to solve this problem came together in a way that really illustrates how distant parts of mathematics can interact with and benefit each other. The method of convex integration started with Nash's work on C1 isometric embeddings in differential geometry. It spread to geometry and topology with Gromov. And it was later connected to microstructure and crystals and differential inclusions in the calculus of variations. And this connection made it possible for De Lellis and Sekal-Hidi to eventually interpret the Euler equations as a differential inclusion and to initiate the applications of convex integration in fluid dynamics that we're talking about today, these crazy constructions. It's also really interesting to look back on the first compactly supported Euler flows that were constructed by Scheffer and Schnirelmann, because if you look closely, you can see that the proofs were actually convex integration constructions in disguise, even though they were not called that at the time and they weren't as systematic and sharp as the methods we're using today. In the future, I'm hoping we'll see a lot more of the difficult unsolved problems about weak solutions in fluid dynamics resolved. And among them, one of my favorite problems is the non-uniqueness of weak Euler flows below the C1 threshold. The solution of Osiris conjecture proves non-uniqueness below C1 third, but it would be really excellent to develop an argument that reaches into the regime where all weak solutions are required to conserve energy, since so far convex integration hasn't been able to access that regime. Yeah, thank you.
Thank you to the Clay Foundation for supporting mathematics. It's very welcome. And I'm very grateful to family, especially to my wife, Simona, for putting up with me many nights of working and Skyping with Tristan instead of talking to her. And it's amazing to receive recognition from people who, when you grow up, you admire so much. A lot of them are in this room, and I'm grateful for that. And I want to just say in the end that I've never written a paper by myself. I was just fortunate to work with really brilliant people, and I'm grateful to all my collaborators for teaching me many things.
So thank you all for contributing to a great day. I do want to say thank you to Michelle here at INES, who's done so much to make this happen today. I'm not sure she's within earshot, but let's give her a round of applause.